is represented by the positive and negative. When you add up all these, it might tend to become 0. If it becomes 0, would you really understand that there is no error in our prediction? No, right? Because there is possibility of error. We always, as statisticians, we always give room for the possibility of error. So this difference or the presence of error has to be captured. That is why, as a convenience, we, instead of taking yi minus y cap, where y cap represents the predicted values, we go for the squares of the errors. So that is what OLS does. Now, in a multiple linear regression model, we can also represent the data in a matrix form, which is given by y is equal to x beta plus epsilon, where y is an n cross 1 vector of observed responses, x is an n cross p plus 1, where p is the independent variables coefficients and the plus 1 is corresponding to my intercept. And beta is a p plus 1 cross 1 vector of coefficients. Epsilon is an n cross 1 vector of random errors. Now, if I have a multiple linear regression, or if I have a data set which has one dependent and multiple independent variables, how do I mathematically calculate the beta? I would be getting the beta using this particular formula here, which is I have the X matrix. X matrix is nothing but the values that you have in the independent variables. You write it down, you get a matrix, you take the transpose and you perform this operation in R or Excel. If it is a, suppose you have more than 3 independent variables, until 3 it is okay to perform it manually, it is easy. But more than 3, you will obviously seek the help of a software which will make your things easy. So this is the equation to find out my beta matrix or my estimates. Once I have got these estimates, I will fit the regression line and I will get to know whether my regression is a good fit or not. Now, there is a very much of an attractive property about OLS that is called BLEU. What does BLEU mean? BLEU means it is best linear unbiased estimator. Why do we call it best? You might think, is OLS the only way of estimation of parameters? No. OLS is not the only way of estimation of the parameters for a regression model. You can also go and look that in literature we have other methods. For example, maximum likelihood estimation. It is also a way wherein we can estimate the beta parameters. But you see that out of all the methods, there is something called the variance that it is giving. The variance that the OLS estimators give is the least among all the various linear unbiased estimators. That is why we opt for the method of ordinary least square estimation for the estimation of parameters. Now, this solution allows us to estimate the coefficients of a multiple regression model, assuming the required conditions hold. Okay. Now we will come to a very important part of our talk, which we are going to deal with is outlier. What do you mean by an outlier? Anyone? I mean, you have the slide already in front of you. Still in your understanding?
A value which is very different from the rest of the data.
Yeah. So if you have a, yeah, sorry.
It's the very extreme points or extreme factors which is nowhere related to the data and which can skew the results also.
Yeah. So from this definition that the person has responded itself is clear that outliers play a very important role when you're trying to build a model, because she said a word that it can skew the data set. So a presence of one outlier or one extreme value can have a very high impact on my data set. Now that is something that we have to deal with, right? So how do we deal it? Before going that, we'll see an outlier is an extreme observation. They are also data points that are not typical of the rest of the data. If I have a set of data and I see that most of them are clustered around the number 50, but I will have some points which are somewhere near the 90. So that is something that I have to see. Okay, what is happening here? Should I really have it in my data or should I remove it? That is what we will start to do in the next slide. Now, residuals against predicted or fitted y values and the normal probability plot. So, how do we understand if there are outliers in my data? You should have some kind of a method, right? You can't just say that, okay, I plotted this data, I saw some points are lying so far, now that would be my outliers. I mean, as statisticians, I don't think that is a scientific way of deciding whether a point is outlier or not, right? So we will see how can we identify outliers and what can be done to treat these outliers. So there might be several reasons for the occurrence of outliers. So these are some of the reasons. Why do you have outliers in your data? Faulty measurements or analysis, incorrect recording of data, failure of a measuring instrument. So these are some of the common problems that give rise to presence of outliers in my data. But you should also remember or have in mind that outliers, if these three are not the reasons for your outlier and you tend to have an extreme observation in the data, you should think whether it should be retained in the data or whether it should be dealt with. Now we have identification of outliers. You have various statistical tests proposed to detect outliers and whether you will have to reject them or not. First one is the residual analysis. What do you mean by residuals? Residuals are nothing but the difference between your original observations and my fitted observations. So I will understand how is my residuals performing. I will take into consideration standardized residuals, studentized residual. These are the two kinds of residuals I have. Now what do I do? Standardized residuals are nothing but residuals which are standardized by their standard deviation. So any residual greater than plus or minus 2 or plus or minus 3 is considered a potential outlier. What do you mean by standardizing? We subtract the mean and divide it by the variance to get the standardized residuals. Next comes studentized residuals. Similar to standardized residuals, but adjusted for varying variances. So, I told you that there is an assumption of constant variance. But in reality, we see that the variance of the residuals is more or less dependent on my x variables. So in reality, I will not be able to attain the constant variance property of my residuals. So we have introduced something called the studentized residuals. And it is created or it is constructed by adjusting for the varying variances. A common rule is that values exceeding plus 3 indicate outliers. So if you have calculated the studentized residuals and if you see that any value is greater than or less than plus or minus 3 in both the ends, the corresponding y will be your outlier observation. That is how you will identify. Next comes the Cook's distance. So this is something that we will be doing in R. That is, Cook's distance is calculated using this particular formula. And if the Cook's distance is greater than 1, it suggests a highly influential observation. That is, the distance is calculated for the residual and the corresponding y should be taken for the understanding that it is an outlier, because the scatter plot contains not the residuals but the observations. Then you have Mahalanobis distance. So it measures the multivariate distance of a point from the mean of the predictor variables. Larger values indicate potential multivariate outliers. The threshold is often based on the chi-square distribution with p degrees of freedom. Now, so this is what I had to share with you before we move on to some hands-on experience in R. Now you can ask me for any doubts or clarifications. We can dedicate like 2 minutes for it. If you don't have any, we will move on to some practical applications and we'll see how can we do it on R.
Hello, ma'am. Good evening.
Good evening.
So my question is, in real life, we have let us say we have been borrowing secondary data sets from let us say a client source. They
Yes.
might be having lakhs of data sets, lakhs of observations
Yes.
with so many number of independent variables.
Hmm.
So if we have a very large data set,
Hmm.
and if there are potential outliers, do we have to follow all these, like for each value or each parameter? Do we have to find the outliers? It will take a lot of time, right?
No, see, this is the process in which or by which we calculate the outliers is already there in R, which will not take even a minute to calculate and give you the number of outliers. And removal of it is also possible in R, which will also not take much time. So for every parameter, it will calculate the distance. Maybe I will show you. Sorry about that. We will have an example that is there in R, and I will show you how to calculate these uh, outliers and how to deal with them and build a better model, which will hardly take you like say 5 minutes, however big the data is.
Okay, thank you.
Ma'am, I have one question.
Yes.
Ma'am, you spoke about the OLS method.
Yes.
So, is it like, so far what I have understood is like it's the best method in the regression?
See, OLS is one of the very conventional methods we have, and in any kind of regression, what we are aiming at is we want to reduce the variance.
Yes.
So OLS, out of all the various other methods, it's since our aim is to reduce the variance, it will help us in doing that. But other types of methods, say maximum likelihood estimation, it will also give me unbiased estimator, it will give me linear estimator and all that. But the variance that it gives, that is when I'm estimating my beta parameters, I should get the parameters. I will use these parameters to give me fitted y values. When I take the variance of it, it has to be as minimum as possible. So among the class of all unbiased estimators, OLS method gives me the estimators with least variance. That is why it is considered as one of the most sought out method for regression analysis.
Okay, ma'am.
Yeah. Anyone else? If not, I think we can move on to the hands-on in R. If anybody has a laptop and if you are ready to work on, it would be a simultaneous workshop so that it will become more interesting. The code will be displayed so that you can run it on your system. Is the screen visible? Okay. So we'll be dealing with 3 data sets, and we'll start with the very basic thing of understanding a data set, building a scatter plot, estimating the parameters, dealing with outliers. Let's see how to go about it. Now, anybody who is not familiar with R, I will just give you an overview of it. So this is how the R Studio platform looks like. So R Studio is a platform which is built for programming. Statistical analysis way easier than the manual way of dealing with statistical analysis. It is not just a specifically statistical software, but it caters to various needs of the statistical analysis also. So the one that I'm working on here, you can see, so the code, it is called the script. So these 4 parts that you see here, these are called the 4 panels of R Studio. This is the script. This is the one where the cursor is now blinking is called the console. Here on my right, upper right, it is my environment. And here I have my help. I just don't have the help. I have the plot, or this is the place, or this is the panel wherein most of my plots are exhibited. So we will start with, now I am clearing all the memory. Now I'm starting afresh. That is why we are making use of the first code. Now for the data set that I'm going to use, that is the stars CYG data, I have to make use of a package which I am using the code install.packages of robust base.
Excuse me, ma'am. Sorry to interrupt.
Yes,
Can
it's
you
okay.
please zoom in your screen?
Sure, sure. How? Just let me know when it is apt for you to see. Let me zoom. View and zoom in. Okay. How much? How good is it now?
A little more? Yes, ma'am, it is good. Thank you.
It's perfect. Can you see the code? Yeah. Okay. When the output is displayed, maybe I will have to. Okay. Let's just have it like this. Okay. So I have my packages installed, and I have my, once the package is installed, I will have to load it also. Only then I will be able to access the package. That is why we have the library. Now, this is the data set that I am going to work on. Here you can see that this data set has observation. Now, in R, whenever you are accessing a data set, you might not know the description about it. So this is the code with double question mark and the name of the data set. If I run this, I will be able to get the description of it here. And if I click on this, you can see a pop-up which talks about the data set. See, here is the description. So this is a very useful tool in R, wherein you are accessing data sets. You might be research scholars trying to apply your theory in various data sets, and you might be wondering what is it. So in R, you have all these data sets along with the name of the variables and what does each of it mean. So now this data set, it is called stars CYG data set. Now what is the data set about? So it has two variables. One is the log.te and the other one is log.light. So both of them are the logarithm type of data, and TE represents the temperature at the surface of the star. Then you have the log light. Now here we take the temperature and the temperature as the dependent and the light as the independent variable. Okay. Now let us also get some of the statistics about the data, the dimension. So there are 47 rows and there are 2 columns. Now I just want to understand how is the data spread. This is my plot. Sorry about it. There is some. We just try to run it again. 1 second, give me 2 minutes. Zoom that. Okay, is the, okay, the presentation is not visible. I hope the plot is visible. It was because I had zoomed the R, that's why it did not hit. Yeah. Can you see the plot? I hope you can see it. So this is how you just plot the data set and you understand how spread the data is. Now from this, you might not be able to get a very good picture. So what we do is we run the histogram to understand how is the data spread. This is the histogram of the data, and I also have an option to draw the frequency polygon over the histogram. And there is another way that you can understand about the data is the quantile plot of the data set. There is a line. So this helps to understand if my observations are normal or not. Now, the normality of the observations is a very important thing that we have to do while we are doing a regression model. Now, by seeing the plot, we cannot understand if it is completely normal or not. So we will have to go for a test. There is a test in R which gives you the normal to check the normality of the data set, which is given by Shapiro test. So this is the Shapiro-Wilk normality test. So I am trying to understand if my dependent variable log light is normal or not. Now since this is a test, when you are always thinking about a test, there will be a hypothesis attached to it, null and alternative. What does my null hypothesis say? My null hypothesis says that the data set is normal. Now what does my p-value say? P-value is 0.52, which is a value which is highly greater than my level of significance. In general, I assume my level of significance to be 0.05. So this p-value is greater than 0.05. So I will reject my null hypothesis and I will say that yes, but here if you see that this p-value is greater than, so I will accept my null hypothesis and I will say that yes, the data set is normal. I will confirm with this test. Now I'm plotting it again. I will tell you why. Now, yes. So this is the code that you run to get a regression model in R. LM of my dependent variable log.light. This tilde is a symbol which can help you understand the left of it is my dependent and whatever variable I give on the right is my independent. So what is this dot? This dot is a way which I give, is a method I give it to R so that R understands that I have to take all the variables in my data set except log.light as my independent variable. So this was devised to give a generic form of the LM model because we are not always going to deal with one independent variable but multiple independent variables. So I have run the model. See, the model gave me the coefficients. This is the coefficient log.te. It is the value below it minus 0.4133. So what does this actually mean? An increase in the value of my temperature, there is minus 0.41. That is, there is a decrease. This minus represents that there is a decrease in the light intensity of the star. As the temperature increases, the intensity at which the star emits light decreases by 0.41 units. That is what this coefficient means here. Now, for my data set that I have plotted, I fit my line. Once these estimates are found out, I create my model. Y cap, I get the predicted values. Once the Y cap are found out, I will use the X and the new Y predicted YIs and I will draw this line. So this is the fitted line I get here. Okay, it looks a little weird. Let's see what is the problem. Now, I get the summary of the model here. This is something that you will have to very much be careful and you have to understand a lot about the summary of the model. In the summary, you can see you get the estimate value and here you have the probability value. Now, this probability value tells me how significant is my independent variable in is explaining the dependent variable. We have two other things, which is the multiple R square. you can see that it is 0.04427. So what does multiple r square mean? So r square is a way, or it is something that is used to explain the variability in my dependent variable using this particular independent variable. That is, only 4% changes in my dependent variable, that is in my log intent light variable, is explained by the temperature. So if I am considering temperature as an independent variable to explain my log light, how good is it explaining the changes in the value of y? It explains only 4%. But logically thinking, or if you ask any person who is doing physics, he or she would say, no, but I think that the temperature is a very good variable that I can take to consider the light emitted by a star. So we should see, okay, my domain experience or the domain knowledge tells that this is not a good thing, because this 4% means that only 4% variability is explained. So if you say that, no, no, I will not take temperature as a good variable to explain the light intensity, but it is not the correct thing. So we will have to revisit our data. What is the problem here? In the data, if you see, there were some points which were far away from your usual points. If you see these round circles here, you can see there are some points which are very far away from the usually clustered points. Now we told that these can be called as extreme observations or outliers. So these might be playing a crucial role. Let us see if we can do anything about it. How do we go about? We saw there are some methods how we can understand whether it is outlier or not, and one of the methods that we use here is the Cook's distance. So as we already saw, the formula calculates the distance, and if it is greater than 1, it will consider it as an outlier and it will give the number of outliers. Okay, so again we have the data, we run the model, we have the Cook's distance, we run the Cook's distance for the model, and we plot. Now we have the line. This is my line of reference. Now R will take the values which are above this line as outliers, and it will give me how many outliers are there in this first iteration. There are 4. Now I will remove all these 4 points, and then I will have the data with, I had how many observations initially? I had 47 observations. Now I am 4 less than 47. So I have 43 observations. With these 43, I will run the next model. Now again, I have another outlier. How many of it is there? 1 outlier based on the second iteration. Again, I will run. Now we will have to see when should we stop, right? We can't keep going on infinitely. When should we stop is when we get the number of outliers to be when we have the number of outliers to be 0. That is when we calculate the Cook's distance, none of the distances should be greater than 1. That is where we stop. Okay. Now we have the new data set, modified data set. Now, what is the dimension of the modified data set? 38. So, if you see, out of the 47 observations, there were 9 observations which are outliers, and it was creating a problem in the summary or in the model fitting. Now, I plot my data. I run the model again using the 38 observations. And if you see that, now if you look at this fit, you can see that the line is almost passing through these points. There are some variations, but it is way better than what it was before. Now, if you see the summary of the model, this is where you will have to see that the variance that the temperature explains the light intensity is increased to 60%. That is 60% of variation in Y is now explained by my temperature. So it matches with my domain knowledge, and the problem that was being caused is because of the outliers. So this is how we work on a data set. Now this is a single independent and single dependent data set. Now we will move on to something which is a multiple data set. which is the
Excuse me, ma'am.
yes.
Will you please be sharing this code with us?
Yeah, we can share. We'll
Yeah, please do it. Thank you.
we'll share it in the email with you.
Yeah, please, please.
Yeah, sure.
Because simultaneously doing this is
Yeah, I
a
am
bit
actually moving a
complicated.
little fast because lack of time. We have another session at 7, right? So I am just skipping, but we'll share the code. You can run it at your convenience.
Yes, please share. Thank you.
Sure. So we have a data set here, which is Anscombe. So what is the data set here? Let us just see about the data set. So this is the data set which has 51 rows, that is a total of 51 observations, and there are 4 columns. So there will be one dependent and there are 3 independent variables. So what are they? So this data tells the expenditure or the expenditure that is spent on education according to for each of the states in the US. That is what the Anscombe data tells me. Now you have the dimension of it, 51 rows and 4 columns. Now my dependent variable here is education. That is amount that is spent on education. I have the histogram, I have the plot, I have the Shapiro. Now if you see here, I said that normality is a very important thing. 0.01 is a value which is less than 0.05. So you will reject the null hypothesis. But we have a convenience here. We have 95% confidence, we have 99% confidence, we have 90% confidence. So to my convenience, I can also look at it as a I can compare this p value not just with 0.05, but I can compare it with 0.01 also. If I compare it like that, it is a value which is greater than 0.01 because it can be approximated to 0.02, and I can proceed with linear regression. So this normality of y is very, very important. So now I am tweaking this p-value according to my convenience. It is not just you can't call it a manipulation, but it is a convenience because real-time data hardly aligns with your assumptions, right? So I can proceed. I run the model here similar to, yeah. So this is the case of the scatter plot is not just a one, it is not one against the other, it is one against many. So you will have a scatter plot matrix. So this is with education, income, whether it is young or whether it is an urban place or not. These are all my independent variables. I have the, if you see here, these are, yeah, here it represents the correlation. You can understand whether there is a positive correlation between education and income, or whether there is a negative relationship, or the relationship is kind of random, wherein there might not be much of an effect. This plot tells you that. So once that is also run, we will go on with the model. We have the summary. See, you have the coefficients here. So that is an increase in the income by 1 unit increases only 0.08 units of my education expense. I have the summary of model. I can see that my R square is 66%, adjusted R square. So you can say that, yeah, it is not a very bad model like the previous one. It is a good model. But we should always remember that not just getting a very high R square in the first go is our goal in making a regression model. It should actually mean whether we are also trying to satisfy all the assumptions. Now we will have to check for any presence of outliers also. I will calculate the Cook's distance. When I calculate, I will see that I have 4 outliers in the first iteration. I proceed. Then I have the second iteration giving me 2 outliers. I have my third iteration giving me 1 outlier. And finally, I end up with fourth iteration giving me no outlier. So I am left with the data set now, and I have 44. So initially I had 51, now I have only 44 data points. I run the model again and I get the summary, and look at the summary of the model. You might wonder now, it was 66% of variation that was explained before, but now it is 64. This is where I would like to emphasize that getting an R square which is as high as possible. And I forgot to mention R square should be a value between 0 and 1. We should not aim at getting 1. We should aim at getting a value of R square which should match your domain knowledge, as well as statistically it should be proved. That is what we are aiming. So a decrease from 66 to 64 is not a, it does not show that the method of removing the outliers is wrong. It just emphasizes that removal of outlier is required to get the best from the data set. So this is what I had to share with you about the conventional methods of doing regression with respect to outliers. So if you have any doubts, we have 1 minute so that at 7 the next session can begin. Or we can go ahead with the next session and we can have some questions at the end.
Excuse me, ma'am.
Yes.
So now when we are dealing with the outliers, what does the code do is to remove them.
Yes.
Right. So when in real time data, if it is very crucial data, let us say something related to health and all, we just can't ignore the data points, right? Like each of the data point is very much valid that like the remaining.
Yeah.
Just because they are somewhere outlying doesn't mean we can just remove them. How can we deal with such kind of data?
Yeah. So now, like the answer to your question is very much in the next session. So I think you can just wait for like 5 minutes so that ma'am can start explaining what would you do if you are dealing with such a situation, which is a very, very important question. And that is why we have more methods. So that will be dealt with in the next session. Okay.
Okay, ma'am.
You can just wait for like 5 minutes. She will introduce you to that.
Sure. Thank you.
Yeah. Okay. Anything else? If not, I would like to ask Dr. Kalevani ma'am to take over the session. Thank you for the interaction. And if you have any doubts, you can reach out to me through the email. I would be happy to reply.
Thank you so much for your time, ma'am.
Thank you. Yeah. So over to Dr. Kalevani. You can start.
Good evening, all. So, myself, Kalevani, Assistant Professor, Department of Statistics and Data Science. So, hope you all have learned about the linear regression modeling, the least square estimation, the assumptions, everything, and how you can do it in R also, right? So, till now, we have worked with two data sets. So, one is star CYG. So, in that data set, the data set follows normality and also the presence of outliers is there, right? In the second data set also, it follows normal, but it doesn't follows normal if you are taking 5% level of significance. For your convenience, you are taking it as 1% and you are doing the least square procedure, right? But in real-time scenarios, so we hardly get the data like it follows normal and following all the assumptions, right? So for these cases, what is the best method or a reliable method you have to proceed? So that is called the robust regression. So before going to going for the robust regression, so first we can see about what do you mean by robust and what do you mean by robust statistics and robust regression, right? So how many of them has already heard about robust statistics? Can I get any replies, comments? How many of them has already heard robust statistics or robust regression?
Ma'am, I haven't heard of robust regression or statistics, but I have heard of robustness check, where one method is checked to see how reliable it is, or it's a cross checking with the some other method.
Okay, then. So we are going to say about So first, robust means what does that word says? Word itself says what is the meaning of that?
Robust is strong.
Yeah, absolutely. Then any other answers? Yeah, so robust means strong. So it is reliable. So we can see the next resistant, stable, reliable. So this means that what are the data may be like. Okay, so in all the situations, like whether the data set contains outliers or whether the data doesn't follow normality or it doesn't follow any of the assumptions, we can go for robust procedure. It will give you a strong or a better result as compared to the OLS procedure. So the term robust generally refers to the ability to withstand or perform well under varying these conditions like outliers or some of the deviations from the assumptions, right? So this is a basic definition of robust. Then we are going to robust statistics. So robust, and the word was first introduced to the statistical literature was in the year 1953. So in statistical procedure, we have some of the location parameters, scale parameters, and regression parameters, right? So in statistics, we will call the mean as a location parameter and scale standard deviation as a scale parameter, like that. So like that, after that in 1954, they have some other authors. Many authors have moved forward for the robust statistical development procedures like location, scale, and regression parameters. So now this session we are only dealing with the robust regression procedures. So before going into the robust regression procedures, we just have a bit of like what is the location in robust and what is the scale parameter in the robust statistics, right? So first, the robust statistics is mainly focused or motivated to two types or the two motivations we have. So the first motivation is to produce a statistical model that are not unduly affected by the outliers. So for we are very much concerned about the outliers. You just see in the first model or the first example, ma'am has noted that star CYG. So because of that four outliers, we are getting a wrong results, right? So the model itself we will see in the R code. Okay, so hands on. So that is very much affected because of that four outliers. So robust statistics is very much concentrating on first our motivation will be the it is unduly affected by the outliers. This is our first motivation. The second motivation is to provide methods with good performance when there are small departures from a parametric distributions. Like if you are we are taking a least squares, we have some of the assumptions like linearity, normality, homoscedasticity, some of the other assumptions. So this is a second priority or the second motivation. So why we have to use this robust statistics, right? So for the first motivation, if the data set contains outliers, how to deal with it. And the second, so if the assumptions, if the data set doesn't follow some of the assumptions, how to deal with it. So for this cases only, the robust statistics is mainly focused. Okay. Then, in statistics, classical estimation methods rely heavily on assumptions that are often not met in practice. So, unfortunately, when there are outliers in some data set, so we can't say that the data set shouldn't have an outlier, right? So, if some of the outliers are present in the data set also, so the least square performance or any classical estimators have give you the poor performance. So, what then we have to go for? So, what are the before going into the robust regression? So, what are the limitations of OLS regression? So outliers is a very major issue because of some observations or some extreme values, the answer may misleading results. So OLS is very sensitive to the extreme values and heteroscedasticity. If you're not getting a unequal or a equal variance, so it tends to heteroscedasticity. There also the OLS results will leads to a misleading results and non-normal errors, multicollinearity. These are the things which already discussed in the assumptions. If these are the things are not invalid, okay, so where the robust regression techniques address the problems by using the weighted loss function. This is very important. This is how we are dealing with the robust regression techniques that reduce the impact of extreme values. Why we have to go for robust regression? So the ordinary least square estimates for linear regression are optimal when all the regression assumptions are valid. So all the assumptions are optimal or all the regression assumptions are valid, then only the regression values will be optimal, and also it will give you a stable result or a reliable result. If any of the outliers are present in the data, so it will gives you the perform poorly. Okay, otherwise it will give you misleading result. So it is why, because that LS procedure is very extremely sensitive to the outliers. So robust regression method is an alternative to least square regression by requiring less restriction assumptions. So if you're truly speaking, there is no assumptions in the regression procedure, robust regression procedure. If you have to any type of data, whether the data contains outliers or it doesn't follow any of the normality or doesn't follow any of the things, we can go for the robust regression procedure. It will give you a best result. I will tell you why it is giving you the best result. So robust regression method focus on estimating the regression parameters in a way that reduces the influence of outliers and unusual data points that might distort the model's accuracy, right? So one student has correctly asked that if in a medical scenario that there are so many observations, okay, so how we have to remove out outliers, because in the star CYG dataset itself, that 47 observations are not only the number, the 47 stars in the direction of the sickness. So that 4 or the 9 outliers is also the stars, the original stars, it is in that direction. So that is also one observation or the information about the whole data set. How we have to remove or omit the data set. So whether that OLS, by removing and again doing the OLS procedure and getting a R-square value or performing the model, whether it is a good type or whether it is a good way to proceed? No, right? We are removing some of the observations. So that is also a part of the whole data set. We can't able to remove as it is. So in that scenarios, we can go for the robust procedures. So you just see that's an example for outliers. So the green points are like it is nearby. Okay, the majority points are here. The red points are scattered somewhere. So it is called the outliers. So outliers in the sense, here majority of the people are on this side. So only 4 of them are that side. So here in this picture also you can find out what is outliers. So next, properties of outliers. So here in this robust regression procedure or robust statistics, we have 2 properties. One is called the breakdown point and another one is called the influence function. So first we will see about what do you mean by breakdown point. So breakdown point is a maximum proportion of contaminated data an estimator can handle before it gives arbitrary large values. It means how much the estimator can able to handle before it goes for arbitrary errors. We will see one example, then you can understand in a better way. See, we are have given 2 examples. So first on the left hand side, see x is equal to 2, 3, 5, 6, 8. In the second right hand side, you just see x is equal to 2, 3, 5, 6, 100. So in the first example, could you see any outliers present in the data set? Shall I get any comments? The replies?
Ma'am, in the first one, there are not such any extreme outliers.
Yeah, but in the second right hand side,
The second one has a extreme 100 value, which is
100 values, right? So if you find the mean for both the scenarios, you just see what is the mean value for the first example. It is 4.8. So while you are calculating the mean value for the second example, it is 23.2. So it is drastically changing while you are changing one single observation. It is just an example with 5 observations. The same scenario will happen for if you are taking 1,000 or 10,000 size of the observation. So while you are finding the median, so what is the answer for first example? It is 5. And for the second example also, the median is 5. Why? Because in mean, if you're calculating the mean, if you're changing a single value, it will be affected, right? It will be affected your answer. It means that the breakdown point of mean is 0. It is very sensitive to extreme points. But whereas in median, If you're like median, how you will find first median? First arranging the point, the middle point, middle value is called the median, right? So if you're the 50% of the observations are contaminated, then only your median value will get changed. So the breakdown point of median is 50%, whereas the breakdown point of mean is 0%. So see, mean is very sensitive to extreme values. That's why the breakdown point is 0%, whereas in median, it is 50% of breakdown point. That's why in robust statistics, we are taking median as a location parameter. But whereas in the classical procedures, you have read about so many distributions also, we are taking the mean as a location parameter. But in robust statistics, wherever you are saying the robust statistics, we are only focusing on median as a robust, more robust. That's why we are taking median as a scale location parameter in robust statistics. Then we are moving for the influence function. So influence function is nothing but how impact the one single data point to a whole estimator. It is related to the breakdown point only. So it helps in accessing the sensitivity of a statistic to extreme values or outliers. A bounded influence function indicates that the statistics is robust to outliers. We can say the median is a bounded influence function, so it indicates a robust. That means it's robust to outliers. But in the function is unbounded in the mean case, so we can say it is less robust. So this is called the influence function. So moving to the next point, what is classical versus robust? That means now we have gone through, no? So in classical techniques, we are seeing the location parameter is mean, whereas in the robust procedure, we are taking median as a location parameter because it's having more robust because of some of the examples, right? And scale parameter also in classical procedure, we are taking standard deviation, whereas in robust technique, we are taking median absolute deviation as a scale parameter. So these are some of the introduction or overview of what is robust and what is robust statistics. So then now we are going for robust regression. So as ma'am has already said about what is classical regression and how to deal with the least square OLS estimation parameters, right? So in this first, Huber 1964 has introduced the first robust regression method. Okay, so first robust regression was first introduced by Huber in the year 1964. So it is based upon a maximum likelihood type estimator. That's why it is called Huber M estimation or robust M estimation, we can call it as. So M regression estimation is a robust method for parameter estimation and regression models, particularly designed to minimize the impact of outliers and provide efficient estimators when the data is contaminated with unusual or extreme values. So this before 1960s, the robust statistics like the location parameter, scale parameter has been established. So after 1964, Huber has introduced the robustness for regression concept also. So this mainly focused or designed for when the data set contains outliers or it doesn't follow any of the assumptions, this procedure will work well. An M estimator is a type of estimator that minimizes sum of functionals of the residuals. Now we will see about what is the objective of the M regression. In least square regression, what we are focusing on, we are trying to minimize the error sum of squares, right? But in the M estimation, what we are trying to do is we are minimizing the sum of functionals of the residuals. We will see. So the general objective of the M regression is minimizing. We are minimizing the sum of function of the residuals. Here, the theta cap is the estimated parameters. Rho of Ri is the weighted loss function applied to the residuals. What is residuals? The observed minus expected or the fitted value is the residuals of each data point. First, we have to find the residuals of the linear model. Then we are going for the weighted loss function. I will tell you how to find that weighted loss function. And by that, we are taking a sum and we are trying to minimize that. This is the main objective of the M regression. So N is the number of observations. Here, a rho function will be a weighted loss function. Here, today we are going to deal about only with the Huber loss function. In robust procedures, this is the first robust regression procedure, no? So Huber has started or established or introduced the first weight function. It is called, or first regression method. It is called Huber M estimation technique. So in that, we are using the Huber loss function. Instead of that, we can able to use Tukey loss function or Hampel loss function also. Today, we are only deal with the Huber loss function. What do you mean by Huber loss function or a weighted loss function? So this is the Huber loss function. So we are giving, you just assume the star CYG data set itself. In the data set scatter plots itself displaying that 4 are in the left hand side in the Y space. It is the outliers. Okay, by visualizing it, then itself you are can able to find these 4 are outliers. Then removing that outliers, they again next 2 or 3 will be the outliers, right? Then what does the actual OLS procedure is doing? Why for that the fit should be like that? Because in OLS, it is giving equal weight to all the observations, whether it is deserving that weight or not. It is giving the equal weightage to all the observations, whether it is extreme observation, outlier, or whatever it may be. But in the robust procedures, what it will do is it will give you a more weight to the majority of the data where it is scattered. It is giving you the less weight to the extreme observations on the outliers. So we don't want to remove the outliers. We are giving a less weightage. That is also an information of the data set, but we are giving a less weightage to the extreme observations. But we are focusing on the majority of the data points. So that's why we are giving a more weight. We are giving one to the points where the modulus of Ori, the residuals will less than or equal to based upon the data. C is a constant here. Based upon the data set, based upon the size of the data set, the C will get changed. And if that residual is greater than C, the weight will be like this. So based upon that, we will get a best model in the robust procedure. So obviously, the residuals, those who are having a large residuals in the sense, the points will be in the extreme observations, will receive the less weights, right? So this is how the technically or the theoretically the robust M regression will perform. So now we are moving for the hands-on of robust M estimation. See, first ma'am has done for star CYG dataset and also for the Anscombe dataset, right? I'm just dealing with again the star CYG dataset. Okay. So what is the description of this data set? So it have a dimension of the data set. It has 47 observations. The 47 observations are the stars in the direction of the sickness. So your dependent variable is the log dot light and your independent variable is log dot temperature based upon the temperature. So the log intensity we are going to predict, right? So we will see the plot of the star CYG data set. By looking into that plot itself, you can see how the trend or the how the fitted line will be. Correct? So majority of the points are in this side only. So only few points are taking place on this side. So by visualizing the scatter plot itself, we can able to find there is a relationship between the X and Y variables, right? So we have done the histogram and the QQ norm and also the Sapiro-Wilk test. So in that Sapiro-Wilk test, for this data set, you got more than 0.05 percentage confidence level. That's why you are accepted. Then it follows normality. Then you have proceed for the least squares, right? So now I'm again fitting the LM model. So this is the AB line of the LM model. Whether this fit is correct or not, can I get any response? whether this fit is correct by looking into the scatter plot, whether it is a correct fit or not, because majority of the points are in this side, then your OLS procedure or the fitted line is showing this line, whether it is correct. No, it is absolutely wrong, right? So then what else we have to do? So that is called the robust procedure. In this case, we have to go for the robust procedure. So the code for the robust procedure is LMROB, the linear model of the robust procedure. So this function is available in the package called robust base itself. So now log dot light is the dependent variable. Again, the still symbol is following that how many independent variables, it will be the dot. Otherwise, you can specify the independent variables also. So data equal to star CYG, method is equal to M. So this is the first method. I already told you that Huber has introduced the first robust regression procedure, that is called M. So followed by Huber, there are so many advanced robust regression techniques is also available, that is called estimation, S estimation, and so many techniques, LQS estimation, everything, LMS procedure, LTS procedure, everything, so many procedures are in robust regression techniques also. We can go for that technique also, but in this today's talk, during the lack of time, I have taken only one robust procedure, that is called M estimation or M regression. So you can next time, or you can go for, or you can do for estimation and S estimation also. Now we are going to do for M estimation only. So I'm just fitting the model based upon the robust model for the whole star CYG data set. I have not omitted or deleted any of the observations. The whole data set, what are the data set maybe, I'm just doing the robust fit. So this is our coefficients. We are getting the intercept and the log dot t. You just see the coefficient itself. You can see here in the LM fit, it is positive in the intercept. By in the robust regression procedure, you are getting the vice versa. We will see why it happened. See, I have plotted the robust regression procedure in a green color. Can you able to see the plot? Yes.
Yes, ma'am.
Okay, so you just see the green line is called the robust fit. Whether it is a correct fit or not? Yes, because majority of the points are here only. But you just see the least square fit, it is wrongly fitted. Because of the 4 outliers, it is fitting like in this way. But it is not a correct fit, right? So we are the whole data set, when I'm going for the robust procedure, so this fit is correct, because, or we can say it is reliable, because majority of the points are on this side only, right? So we just see the summary of that robust model. So before that, so what is the summary of the linear regression model, like OLS procedure? So the summary of the model, the R square value 0.00. That is 4% only. The OLS procedure is telling that only 4% only association between the X and Y variables. But it is not correct. While we are doing it in the robust procedure, you just see the summary of the model. See, the R square, the adjusted R square, it is giving 35% association is there in X and Y variables. So the least square procedure is very sensitive. If any 1 or 2 outliers are present in the data itself, it is like giving you a wrong result or misleading result. So why we have to go for regression? For predicting the new data. So our regression parameters itself is wrong, then how we can predict the new data? So that's why the robust regression came. So this is an advanced procedure to deal with this type of scenarios, whether the data set is having outliers or any type of normality or the assumptions. So then again, for just the enhancement or again to get a better model. So this is also as compared to least square. Now the robust model is a best R square, and also it having a correct. We can also, by visualization also we can tell it is logically also correct, because this fitted line is near to all the majority of the points, and also by seeing the R square also it is getting high. But we can to just enhance the data, we are just removing, we don't want to remove, right? So because in the OLS, after removing only, you are getting like 0.60% as 60 percentage. But while keeping all the observations as it is, in the robust procedure is giving 38 percentage association. So that's why we are telling that robust procedure is better or reliable as compared to the OLS procedure. But we just see while removing the outliers also, after removing the outliers, what does this robust procedure giving? So I'm just, again, by using the Cook's distance, I'm removing the outliers. So again, for the same data set, we have already done this. So that's why I'm just moving fast. So now we have a clear data set, or we can call it as a without outliers data set. It consists of 38 observations and 2 variables. So this is our whole data set without outliers. So we are plotting that without outliers data set. So now the scatter plot is looking like this. Again, we are going for the linear model. Then least squares method. So AB fit. So while without outliers, so removing that outliers, see that OLS procedure turns this side, right? But keeping the outliers as it is also, the robust procedure shown this line only, right? So after removing the outliers, the R square for the OLS procedure is 0.71. Now for robust regression, we just see the AB line of the fitted model. So exactly the same line it is fitting, but the summary of the model is also, we just see the R square. So it is 0.59, that is 59 after removing the outliers. Again, we are doing the robust linear model. So it is giving that 59, that is near to 60 percentage of the association between X and Y variables is given in the robust model. So this is why, so in scenarios like this is how the robust regression is useful, while the data set contains outliers, or while the data set doesn't follow normality or doesn't follow any of the assumptions. So truly speaking, for the robust regression procedures, there is no assumptions. What are the data set maybe, you just go for the robust regression. It will give you a less weightage to the outliers, and it will deal with the assumption. It doesn't follow assumptions also, it will follow. So next we are going for the next data set, that is CARS data set. So we just see the description of the data set. So it is in the data sets package. So it will tell you that the data give the speed of cars and the distance taken to stop. Okay, so here also we have two variables. So one is called the speed and another one is called the distance. Here we are finding first, checking whether this data set is follow normal or not. By using the histogram, we are just checking. So here distance is the dependent variable, because based upon the distance, how much that speed should be there. That is the independent variable. So checking the histogram, this is the code. You just see, by seeing the histogram itself, the data set is skewed, right? It is not normal. I'm just giving the lines. Now we can't correctly say whether it is normal or not. So that's why we are moving for the QQ plot, that is quantile plot, normal QQ plot. So here also I'm making the line. So here also some of the points are not near to that line. So for confirming, we are using the Sapiro-Wilk test. So you just see the p-value is 0.03. So if you are taking 5% confidence level, it is obviously rejected, right? We can't go for OLS. But if you're taking 1% of confidence level of significance, you can work for this data by using the OLS procedure. But in robust procedure, we don't bother about whether it is 1%, 5%, what are the data maybe, what are the level of significance level maybe. Because in medical data, as you said, we can't go for the high alpha level, right? So in that type of cases, robust procedure is best. We don't bother about for what are the level of significance level will be, like 5%, 1%, or what are the percentage maybe. The robust procedure will give you the reliable or a stable or a better result as compared to the OLS procedure. Now we just plot the CARS data set to visualize. So this is how the data set looks like. So this is the speed and this is the distance in the y direction. So this is how the scatter plot of the CARS data set. We are fitting the linear model. You just see. So these are my coefficients and this is the fitted line, because in this data set, we can see that now no observations are in that much extreme, right? That's why it is giving you this correct direction. So then go for the summary of the model. So you can see the summary of the model, that is the R square values 64 or 65. Adjusted R square we can say it is 0.64. That means 64% of the data are explained by associated with the X and Y variables. But whereas we are going for the robust procedure using the M method, see the AB line of that model is slightly different. And also summary of the model, you just see the R square value, it is 0.68. Because this data set, I already told you that the robust procedure, the robust statistics or robust regression, we have two motivation or we have two consideration. So the first one is outliers. First, this robust statistics or robust procedures is mainly designed for to deal with the outliers. So second scenario is, if the assumptions are not valid, then we have to go for, this is the second motivation, right? So the first data set, the outliers concept. So for because of that some 4 or 5 outliers, the OLS procedure is giving misleading results. But in the second data set, we don't have that much extreme observations. We don't have that much outliers, but it doesn't follow normality. If you're taking 5% of confidence interval level of significance, it doesn't follow normality, right? So in this case, this is the second scenario. So how we have to deal with it? So in this case also, the robust procedure is giving you that 68% association, as in least squares, it is giving at 0.65, that is 65% of association. Then we just go for the Cook's distance to removing the observations. So to get a better model. So while keeping the outliers itself, robust procedure is giving the best value only. So we are just, if it is just, it is not a medical data, or it is like if you are thinking that that observation is an unusual observation or some any typing mistakes, if that type of errors can happen, and that may also will be an outlier. In that case, we can able to remove the outliers and we can proceed for the data set. In the CARS data set, I'm just doing the procedure as we have done for the star CYG data set. So in the first time, I'm getting two outliers and just proceeding the next step. So we have to do till no outliers, that is the value should be 0. So now again, we are getting 4 outliers. You just see in this side. So this 35, 39 or the observation number. And again, we are removing that 4 outliers in that data set. So again, we are getting 2 of them are outliers. Then we are proceeding. So now we got 0, right? So now this data 3 have no outliers. Now we are going for the data 3. So we are checking the dimension of the data 3. So in the CARS data set, I think 50 observations in two variables. Now we have 8 outliers are present in the data set. So we are removing that 8 outliers. Now our dimension of the data set after removing the outliers is 42 rows and 2 columns. For this data 3, we are plotting. So this will be our plot for data 3. And for OLS procedure, that is linear model we are fitting. This is our AB line. So the summary of the model is 0.71. That is 70 in the least square procedure. It is giving that 71% association between the speed and the distance. We can see in robust for the without outlier data set. This is the code for M, that is robust M procedure. We are putting the AB line. You just see somewhat it was deviated from the least squares and the summary of the model. You just see it is giving 0.71. So the robust procedure with outlier or without outlier, it is giving a best result or reliable result as compared to the least square procedure. So first data set star CYG, what we have dealt with is, so extreme observations, that is the outlier present in the data, how we can deal it. The second data set, CARS CYG data set. So by the visualization, we can see that that is not that much extreme outlier, but it is an outlier. And it doesn't follow normality if you're going for 5% level of significance. In that scenario also, in that type of data set also, the robust regression is performing good, right? So these are the different scenarios of data sets, how the robust regression procedure is doing good. Now for the third data set, Anscombe data set, we are going to see, ma'am has already described the data set. It is about the education. US state education expenditure is your dependent variable and urban rural income or your independent variables. So I'm just running the data set. So we have already seen that the histogram. So this is our frequency polygon looks like. So we are moving for, we doesn't get that much clarity. That's why we are going for QQ norm. Here also, some of the points are not nearer to that line. So again, for much more clarity, we are going for the test, Sapiro test. So here it is all in this data set also, it is telling that 0.01. If you're going for 5% level of significance, obviously this data set, we can't go for proceeding the least square procedure, right? If you're taking 1% level of significance, we can do the OLS procedure. But in the robust procedure, we can't bother about any of the level of significance, right? So we can do this for, see, just plot this Anscombe data set. This is your correlation matrix. We are fitting the data. This is our summary, right? What is the summary? The R square value is 0.66. For the same data set, what is the scenario of this data set? The value of normal, that is for if you are taking 5%, it doesn't follow normal, then obviously we can't move forward for LS procedure. So then what is the best way, or the next other technique is robust procedure. So we are proceeding the robust technique, robust M procedure. So you just see, these are our coefficients. You just see the R square value is 0.71. So you just see in the least square, it is giving you 0.66 association. But see, it is giving you 0.71 association, right? By keeping all the outliers, by whether this follows normality or not, what are the data set maybe, but it giving you the best result or reliable result as compared to the OLS procedure. Then for to enhance the model or to make it as a little bit better way, we are just removing the outliers, and for that without outliers data set, we are doing the analysis. Let's see. I'm again doing the same procedure, Cook's distance, to remove the outliers. Yes.
நம்ம மட்டும் தான் இருக்கோமா சாட்டர்டே
Okay, sorry for this. Okay. So again, doing for the Anscombe data. So we have to do till the outliers will be 0. So now we got the value as 0. So for the data set, data 3. So this is our without outlier data set. The dimension of the data 3 is 44. So we are plotting that data 3 and we are just proceeding the linear model or the least square for the data set data 3. You just see the summary of the model. The summary of the model R square is 0.64. That is 64% association. But if you're going for robust model, you just see the summary of the model. It is 0.74. That is 74% association. So without outliers. So the main concern or the main motivation of this thing is, so robust procedure will give you a better result under whatever the data set may be like, whether it is outliers present in the data set or if doesn't follow any of the assumptions. So this is how the robust regression performance was good as compared to the least square procedure. So this is what we have taken the 3 data set in different scenarios and we discussed. So do you have any doubts regarding this data sets and the codes and the concepts? Yes.
So far, we are clear, ma'am. Thank you.
Okay. Any others? Yes. Any doubts? Okay, if there is no doubts, we are me and Radha Lakshmi ma'am, we extend our heartfelt thanks and for your patient listening. If you have any queries regarding this data sets or the coding, you can reach us. We will send you the one student has asked the codes. We will ready to share the codes and also the materials in the Gmail. Thank you.
Ma'am, I have a question regarding the next sessions.
Next session. So this is the second session.
Maybe in the flyer when we were applying for this workshop,
Okay.
in the email we got it as every Saturday from 6 p.m. to 8 p.m. But
Okay.
as in the further details, you did not mention how many Saturdays.
This is for only 2 hours.
Okay.
1 hour classical and 1 hour regression.
Okay.
So next Saturdays or next week, some other like resource questions will be there. So our talk is like 2 hours only. It is not like weekly wise.
Okay, so this workshop is only for today
For 2 hours,
and it
yes.
is done.
Yeah, it is done.
Okay. But in the email, it was mentioned that every Saturday from 6 p.m. to